Let's take a look at polynomials. If you break down the word polynomials, it literally means many numbers. What it looks like. Any function in the form ax to the n plus bx to the n minus 1 and so on till you get to a constant number c is considered a polynomial. This n is a whole number and it has to be one or more to be considered a polynomial. They can't be fractions, can't be radicals, just has to be straight up whole numbers. Can't be negative either. So n is the largest exponent of the function and determines the degree of the polynomial. So here we have the degree of the polynomial determines characteristics of the function, such as max number of turning points or maximum number of x-intercepts, and the end behavior. So here we have a fifth degree polynomial. I know it's a fifth degree polynomial because the largest exponent is a 5 there. The other numbers don't matter in determining the degree of the polynomial. So here we have a second degree polynomial, and here we have a third degree polynomial. You'll notice that the 2 here makes it a second degree polynomial, and the 3 here makes it a third degree polynomial. Number of turning points. There can be a max number of n minus 1 turning points. Remember, n is the degree of the polynomial. So with this fifth degree polynomial, we're going to have at most 4 turns. And what we mean by turns is these. 1, 2, 3, 4. Those are your 4 turns. With a second degree polynomial, which you're pretty familiar with, they're quadratics, it's going to have 1 turn at the most. So you can see that we have only 1 turn right here. Then we have third degree polynomials, which look like this, at most 2 turns. So there's your 1, there's your 2 turns. Now you'll notice that I keep using the term at most. It can have less than 2 turns. If it was just x cubed, for example, it would have an inflection point. It would look more like this, where this wouldn't be necessarily considered a turn, more of an inflection. So we can have less turns, but we're not going to have more than 2 turns. Max number of x-intercepts. There can be a max number of n intercepts. So for this fifth degree polynomial, we have a maximum number of 5 x-intercepts. So that's 1, 2, 3, 4, 5. For a second degree polynomial, we're going to have at most 2 intercepts. And we know a lot about quadratics, so you already know that you can have 2 intercepts. You could have 1 if it was directly on the line, or you could have no intercepts if your vertex is above the x-axis and it was positive. So that's why we're using the term at most. Or for the third degree polynomial, we're going to have at most 3 x-intercepts. This one we have 1, 2, 3. Now let's take a look at end behavior. Now we only have 4 different outcomes for end behavior. We have even degree polynomials, right? And you know that this can either be positive or negative. So all even degree polynomials are going to act at the end. It's going to act like x squared. So it's either going to be both ends up with something in between, or both ends down with something else in between. What I mean by something in between is this could go down and then go up and down again, and have something else going on. But basically what's happening is we're only concerned about, guess what? The end behavior. So for evens, it's either both up or both down. For odd degree polynomials, they're gonna act like x cubed, all right? So when I say odd degree polynomials, I'm meaning that n can be 3, 5, 7, 9, 11, whatever it is. As long as it's an odd number, it's an odd degree polynomial. So positive is going to be down and then up. Negative is going to be up and then down. So as we go to negative infinity on the x-axis, y is going to negative infinity. As we go positive infinity on the x-axis, y is going to positive infinity, which is usually how you'll see it written as limits. For negative, it's going up. As x goes to negative infinity, y is going up. And as x goes to positive infinity, y is going to negative infinity. All right, so factoring polynomials. We're going to take 3 steps. First, we're going to find the possible rational roots using the P over Q test. I'll explain what that is. We are going to use synthetic division to check the actual rational roots. I'm going to also show you what that is. We're going to continue factoring until you get a quadratic expression. And once you get that quadratic expression, you're going to factor it using the methods that you already know how. Yeah. Now we have the P over Q test. So any function in the form ax to the n plus bx to the n minus 1, so on and so on, plus c can be written in the form, same form, only we're going to call that first term q and the last term p. When written in this form, all the possible rational roots can be found by dividing all the factors of p by all the factors of q. So here's an example from what we did before. This is probably one of the simpler ways you might see it. For this function, since it doesn't seem to have a p, all you have to do is factor out the x and then do the test. So factoring out the x gives me that, and the factors of p would be 1, 2, and 4. Factor of q would just be 1. And so P over Q, all the possible combinations would just be positive and negative 1, 2, and 4. More difficult example. With this one, P is 12 and Q is 4. So this is P and this is Q. So the factors of P will be 1, 2, 3, 4, 6, 12. Factors of Q are 1, 2, and 4. So here are all the possible rational roots. We have the 1, 2, 3, 4, 6, and 12 divided by 1. We have the 1, 2, 3, 4, 6, and 12 divided by 2. And we have the 1, 2, 3, 4, 6, and 12 divided by 4. So that's all the factors of P divided by all the factors of Q. Factors of P are going to be written down every single time in the numerator. And then the factors of Q, 1, 2, and 4, are written down every single time in the denominator. This to me is the most efficient way to get all of the factors. So just do it in order. List out the factors of P and then list them out for each factor of Q. Now some of these can be cancelled. For example, all of these can just be written as whole numbers because they're being divided by 1. So I usually don't even put over 1, I'm just using it for this example. Now if you look at the second line, 1/2 is a new one, but 2 over 2 is 1. We already have 1, so you don't need that. 3 over 2 is a new one, so because that can't be simplified. But 4 over 2 is 2, and we already have 2, so we don't need that. 6 divided by 2 is 3, we already have 3. And 12 divided by 2 is 6, and we already have 6. So the only useful ones from this line is 1 over 2 and 3 over 2. Now if you go to the third line, we can exclude even more. We have 1/4, that's original. 2 over 4 is a half, so we don't need that. 3 over 4 is original. 4 over 4 is 1, so we don't need that. 6 over 4 is 3 over 2, so we don't need that. And 12 over 4 is 3, so we don't need that. So the only original ones from that third line are 1 over 4 and 3 over 4. So now when I list them out, I have 1/4, 1/2, 3/4, 1, 3 over 2, 2, 3, 4, 6, 12. Now I put them in order. You might not necessarily need them in a specific order, but I tried to just order them from least to greatest, just to be more organized. So, testing the possible rational roots using synthetic division. So let's say we have this. We're going to follow the same steps that we did in order to get the possible rational roots. So we're going to factor out the x. The factors of p are 1, 2, and 4. Factors of q are just 1. And our possible rational roots are positive and negative 1, 2, and 4. So we already have the x factored out, so we're going to concentrate on what's left in the parentheses and test the roots. To do this, we're going to use synthetic division. So let's take a look at how to do synthetic division. So we're going to draw a little L table here, and we're going to leave the x's out and just write the numbers. Now what you'll notice for this is that we are missing some spots. What I mean by missing some spots is, if you look at the exponents, we have a 4, and then there's no 3, then we have 2. So what we have to do is we have to make up for those missing spots by putting a 0. So we have -1 to start off with, then we have a 0 for x cubed, 5 for x squared, a 0 for x, and then just regular -4. Now we have to pick what we're dividing by. Usually I like to start with ones, right? So I'm going to put a 1 right here, and this is how it works. You always drop the first number. And once you drop that first number, to give you -1 down here, you are going to multiply by whatever is up here. So -1 times 1 is -1. And then as you go down, you're going to add straight down. Now what I mean by add is, if it's negative, you'll subtract. If it was a positive number, you'd add it. So 0 plus -1 is -1 times 1 again is -1. 5 minus 1 is 4. Multiplied by 1 is 4 again. 0 plus 4 is 4. 1 times 4 is 4 again. 4 minus 4 is 0. Now, this one happened to work, and we know it worked because the remainder is 0. If the remainder is not 0, you have to try again with a different number. Now we started off with x to the 4. So what this part represents is -1 x cubed minus 1 x squared plus 4x plus 4. All right, that's what that represents. And then what I would do is I would set up another synthetic division using these numbers, same numbers that we have here. -1, -1, 4, and 4. And I would try more numbers. So hopefully this helps you out. If you have any specific questions, ask them in class.